Hi everyone. So today we're going to have a look at the impact of fossil fuel combustion on the carbon cycle and how it impacts upon the flows and the stores within that cycle. So when we look at fossil fuel usage, it's not really been that long in the grand scale of things, in the grand scale of the Earth's time scale, that we've been using fossil fuels, only for the last 2 centuries actually. But coal, oil and gas, the fossil fuels, have driven industrialisation and urbanisation that we've seen in that period. And yes, we are developing renewable energies. We know that we need to, because fossil fuels are finite and they will run out. And they are obviously having such a huge impact on the environment. However, currently, the global economy is still overwhelmingly dependent on burning fossil fuels for energy. When we actually look at the figures, the consumption of fossil fuels releases 10 billion tonnes of carbon dioxide into the atmosphere every year, which increases the amount of carbon dioxide in the atmosphere by about 1 parts per million. Since 1750, anthropogenic, that means human carbon dioxide emissions, are nearly 2,000 gigatons, and 3/4 of these are from the burning of fossil fuels. And when we look at graphs showing the amount of carbon dioxide in the atmosphere, what we have currently is the highest level of carbon dioxide in the atmosphere for 800,000 years. So those are some pretty big figures when we look at them. Where is all this carbon coming from? This graph here is a really nice illustration of where that carbon is coming from. So you can see China, by far the biggest in terms of carbon emissions, followed by the United States. India is pretty big on there, Russia, Japan, and then you can see the developed countries of the world pretty much there, making up the rest, and then the whole of the rest of the world, 15%. So we can see that carbon emissions are dominated by a handful of countries. Did you know that concrete is actually one of the largest emitters of carbon dioxide? So you can have a click on this link and read this story from the BBC News about concrete. If we think about how this material, concrete, dominates urbanisation, we talk about the concrete jungle, the urban jungle, and it's a material that we've used incredibly widely to build our buildings in our urban areas. Sydney Opera House, the Lotus Temple in Delhi, the Burj Khalifa in Dubai, they're all supported by concrete. And so we owe a lot to this material. It's enabled us to produce these iconic buildings. However, it is very, very bad for the environment. And in fact, cement creates about 8% of the world's carbon dioxide emissions. And when we look at it, it is the most widely used man-made material in existence, second only to water in terms of the most consumed resource on the planet. But it's really, really bad in terms of its carbon emissions, and it's everywhere. And then what about flying? This was a story that was in the news a couple of years ago. Prince Harry is somebody who is really environmentally friendly, and he does lots of campaigning for the environment, but he flies everywhere. And this was a story about him taking his private jet to Nice in France to visit Elton John, and they looked at how much carbon he actually created. And for the 2 flights there and back, just to Nice, it's about 1 hour and 40 minutes away by plane, was equivalent to more than 3 times the annual, so yearly carbon footprint of the average Briton, or 58 times the average yearly emissions of somebody from Lesotho in Africa. And that's where Prince Harry went on his gap year and helped with the charities and that kind of thing. So this is a huge impact on the carbon cycle, people taking these private jets very short distances. When we actually look at these figures in more detail, what we actually realise is that anthropogenic or human carbon emissions are actually really quite small compared to the natural flows of carbon that take place. So less than 10% what flows naturally between the biosphere and the oceans and the atmosphere on an annual basis. However, even though they're relatively small, less than 10% of those overall flows, that extra carbon has a significant impact on the amount of carbon that we've got in the atmosphere and in the oceans and the biosphere as well. So despite lots of efforts around the world to try to reduce carbon emissions, they are still growing, and particularly in certain countries around the world. So one idea is, okay, the issue here is we're taking carbon from the fossil fuel, so from where it's normally stored in the rocks beneath the ground for millions of years before being naturally released at a volcanic eruption, for example. And we're taking that store that should be there for millions of years, burning it and releasing that carbon into the atmosphere. Okay, so what about if instead of releasing that carbon into the atmosphere as we burnt it, we captured that carbon that was being released through the burning, and then we took it and we buried it back into the rocks beneath the ground. And this is something called carbon capture and storage. So you capture the carbon dioxide that's being released, and then you bury it, you push it back into the rocks, and you put it back essentially where you've taken it from. And this is something that's really grown. This is something that's really being looked at a possible solution to what we're doing. So far, we've seen this piloted in a few places around the world. So you literally capture the carbon dioxide, you compress it, and then you pump it and inject it into the rocks beneath the ground, where it's then stored permanently. This could be really significant moving forwards. However, there are some problems with it. Firstly, these schemes are extremely expensive, and it's only really the world's richest countries that would be able to afford this kind of technology. Costs for one station, for example, that they looked at for North Yorkshire, more than £1 billion. And you also need very particular geological conditions. You need porous rocks that have impermeable rocks above them. You need very particular geology in order to be able to actually use this technology. So there are issues of cost and there are issues of the actual geology itself. So you'll see I've put quite a few links on there to this, so you can do a bit of reading around the topic. But there are quite a few places around the world now that are looking to do this, looking at turning carbon dioxide back into rock. So putting it back where it was before, taking it from the ground, returning it to the ground. And therefore we haven't got that increase in carbon dioxide going into the atmosphere. Instead, it's going back where it was. So the idea is that this will cause less disequilibrium to the carbon cycle itself. Okay, let's just go back to our positive and negative feedback loops. So I could see from the test too that some of you got a little bit confused with this. Some of you perhaps need a little bit more information about this. Remember, feedback is when a system changes. Something happens to a system that throws it out of equilibrium. And we've got two types of feedback that can happen. So negative feedback is where the change happens and in response it actually manages to counter that change and restore equilibrium. Positive feedback is where that initial change snowballs, and that initial change leads to further change, which leads to further change, and that system sort of gets out of control. So I know that it's quite confusing because you think negative feedback, well, that's going to be something negative. Positive feedback, that's going to be something positive. In fact, it's the other way round. And one way to look at it is to actually think about the sort of mathematical symbols of plussing and minusing something. So negative feedback is where something happens and then there's a minus, and that thing that's happened is taken away again in order to restore equilibrium. Positive feedback, we've got a plus. So something happens and then something else is added to that, and something else is added to that, and the system gets out of control. So that's perhaps a different way to look at it, so you get the two the right way round and don't get confused. In terms of feedback then within the water cycle, so let's have a think of what's happening at the moment. So we've got global warming, and those rising temperatures are affecting the water cycle on a global scale. So in a warmer world, we've got greater evaporation, and the atmosphere is holding more water vapour, which means we've got more clouds, which means we have more precipitation. And that's a positive feedback effect because something's then causing something else to happen and something else to happen. And because water vapour is a greenhouse gas, although we don't often talk about it, we've therefore got more of a greenhouse gas in the atmosphere, which is then causing further increase in temperature. And so you can see how we started with rising temperatures, we've moved to increased water vapour in the atmosphere, which leads to more heat being trapped, which leads to a further increase in temperature. So what's happened is accentuating the problem and making it worse. Positive feedback. But we could also see a negative feedback from this. So because we've got more water vapour in the atmosphere from a warmer climate, we've got more clouds, and those clouds reflect solar radiation back into space, so therefore having a cooling effect on climate. And there's our negative feedback. Something's happened, which has then caused something to take that back again and restore the system to equilibrium. So you've got either a positive or a negative scenario that could happen in terms of extra water vapour in the atmosphere. When we look at a drainage basin, we can have a look on a longer term scale. So when we've talked about this before, we've talked about that balance between precipitation being the input and evapotranspiration and runoff being the output. And in order for equilibrium to exist, we need a balance between precipitation and evapotranspiration and runoff. But this equilibrium varies from year to year. And sometimes we have above average precipitation, and sometimes we have below average precipitation. If we have above average precipitation, we will have extra water in the rivers, we will have more evaporation. And that extra water will recharge the aquifers, will increase those reservoirs of water beneath the ground. And so that then restores the equilibrium to the system. That is negative feedback. During a drought, the system then adjusts and regulates to lower than average precipitation by reducing runoff, reducing evapotranspiration, holding on to the water that it does have. And the water table goes lower, the springs dry up, and all of that water is conserved. So again, maintaining that equilibrium. And if we were to look on the smallest scale within the water cycle, let's have a look at a silver birch tree, one individual tree, for example. If it becomes stressed, if we've got less water than usual, what it does is it sheds most of all of its leaves, and it sort of goes into shutdown mode and holds on to the water that it does have. And that is also a negative feedback loop that ensures the survival of that tree. The water that it does have, it holds on to, and it doesn't lose any water that it doesn't need to. It holds on to what it's got. What about feedback in the carbon cycle? So if we look at the current state of the carbon cycle, we know that we've got a disequilibrium. That human activity of taking the fossil fuels from beneath the ground, burning them, putting that carbon dioxide into the atmosphere, which then diffuses into the oceans and increases the acidity of the oceans. We've got disequilibrium. But within the carbon cycle, there are feedback loops that could, in the long term, act as negative feedback to restore equilibrium, or positive feedback to further accentuate that disequilibrium that we have. So, for example, we've talked about this before, having more carbon dioxide in the atmosphere could stimulate extra photosynthesis, and we call this carbon fertilisation. And if we've got a boost to photosynthesis, we've got extra vegetation, and more carbon is therefore being taken back in from the atmosphere and stored once again. So carbon dioxide is plant food. And if you watch this clip here, the YouTube clip, you will see scientists looking at growing a plant in normal conditions and in higher than usual carbon dioxide conditions, and you will see how much faster and how much bigger and stronger a plant grows with that extra carbon dioxide in the atmosphere. So long term, perhaps things are not as bad as we often talk about. Long term, maybe carbon fertilisation will mean that the carbon cycle will find its way back, will have a negative feedback loop to eventually restore equilibrium. That extra carbon we've put into the atmosphere will increase photosynthesis, will make the vegetation bigger and stronger, which will therefore take that extra carbon dioxide back out of the atmosphere and store it within the biosphere. However, there are other factors that determine how well plants grow. We've got to also look at sunlight, we've got to look at the soil nutrients, we've got to look at water and nitrogen. So it's not really possible to say with certainty that this is going to happen. Positive feedback is also possible, which could lead to greater disequilibrium. So global warming will intensify the carbon cycle, will speed up decomposition, will release even more carbon into the atmosphere from those melting ice sheets. And as the Arctic sea ice and snow cover shrinks, we've got much greater land and sea exposed. It's darker in colour, which means more sunlight is therefore absorbed, which warms the land further, and the remaining snow and ice melts even faster. That's the sort of classic positive feedback mechanism that we talk about in the Arctic. So the ice is white, it usually reflects the sun's rays, but with a warming climate, the ice is melting, the surface below is dark, which then absorbs the sun's rays, which means the surface warms and the remaining snow and ice melts even faster. Okay, so you've got some questions. First of all, to talk about fossil fuel combustion and then carbon capture and storage. You've got lots of articles you can read about that. And then we need to make sure that we've got this positive and negative feedback loop sorted, and we've got some examples of each. And then there are two 10-mark questions here. So the first one at the bottom, examine the significance of the role of vegetation in linking the water and the carbon cycles. And here we've got a mark scheme that you can have a look at. So it's 6 marks for area 1, 4 marks for area 2. So looking at the knowledge in terms of vegetation storing water and also storing carbon, and how changes in vegetation will affect both of those stores. And then also then looking at the transfers of water through transpiration and transfer of carbon through photosynthesis and respiration and the impacts of that. And then the AO2 comes in from evaluating the significance of the role of vegetation. How important is it? So having a look at how the disturbance of systems in equilibrium So reduce water into the biosphere means the plants can't exchange carbon through photosynthesis. But then also having a look at the fact that if the carbon cycle processes like photosynthesis and decomposition stopped, the water cycle would still continue, although its balance would be a bit off. But if the water cycle stopped, if the evaporation from the oceans and the rain down to the land stopped, the carbon cycle would not be able to function. So there is a difference there. So the second 10-mark question, examine how feedback loops can affect the processes and stores within the carbon cycle specifically. So there's two 10-mark questions there. I'd like you to choose at least one of them to do and let me have that answer. Obviously, the most diligent, conscientious of you will do both and let me have those.